So let's say I want to make a fourth degree representation of my function f of x equals e to the 2x. So let's start by writing the general fourth degree polynomial that I want to be finding. So it's going to be a fourth degree polynomial. I'm going to call all my coefficients a, so a sub 0, and then a sub 1x, and then a sub 2x squared, and then a sub 3x cubed, and then a sub 4x to the fourth. Okay, so don't freak out. This doesn't, I know this looks complicated, but really, if you cover up the a's with your fingers, it's just number plus number x plus number x squared plus number x cubed. Just remember, it's a familiar fourth degree polynomial. So I said that the heart of this conceptual process is I want to set the y coordinates to be the same, so f of 0 should equal p of 0. And then I want to set the first derivatives equal. Oops. And then I want to set the second derivatives equal. And so on. So here's what we're going to do. I'm going to calculate all of the derivatives of f down this side. And I'm going to calculate all the derivatives of p down this side. And then I'm going to evaluate them at 0. And then I'll set all those equal. All right, so let's just do the derivatives of f. So this is going to be f, f prime, f double prime, f triple prime, and fourth derivative of f. All right, so f is equal to e to the 2x. And let's just take the derivatives. So this is 2 e to the 2x. This is going to be, let's see, when I take the derivative here, another 2 comes down. So you could write this, well, yeah, let's go ahead and write it as 4 e to the 2x. And then another 2 will come down, so this will be 8 e to the 2x. And another 2 will come down, so this will be 16 e to the 2x. Okay, so far so good. But remember, I want to evaluate each of these derivatives at x equals 0, because I'm setting all of these things equal to each other at x equals 0. So let's evaluate that at x equals 0. So when I plug in 0 up here, I get e to the 0, which is 1. I plug in 0 up here, I get e to the 0, which is 1, but now I've got 2 as a coefficient. It looks like this e to the 2x is always going to end up being equal to 1, because it's always going to be e to the 0. So really, it seems like I can just look at these coefficients. 4, 8, 16. All right, so I'm setting those to be equal to all of the derivatives of p evaluated at 0, and p was the polynomial. So I've already done all the left-hand sides of these equations here. Now let's do the right-hand sides. So I've got that my p to the fourth, my p sub 4 equals a0 plus a1x, a2x squared, a3x cubed, a4x to the fourth. Sorry about that. Okay, so let's take a derivative here. P prime is going to be, so let's see, a sub 0, that's a number, so the derivative of a constant is 0. Here, the derivative of this term is going to be a1. The derivative of this term, the 2 comes down, so I've got 2a2x. The derivative of this term, the 3 comes down, so 3a sub 3x squared. The derivative of this term, the 4 comes down. Let's find the second derivative. So again, the derivative of a constant becomes 0. The derivative of this, the x to the first becomes an x to the 0, so I'm just left over with 2a sub 2. Here, the 2 comes down, so I could write 6, because it's 3 times 2. But I think it's going to bring out a pattern better if I just keep the 2 there. So I've got my 3, I've got the 2 that's come down. Oops, I've got my a sub 3, and I've got an x. So same thing here. I'm going to bring the 3 down. So I'll have 4 times 3, a4, x squared. All right, let's do the third derivative. I've got 3 times 2 times a sub 3, which came from this term. And then here, the 2 will come down. So I'll have 4 times 3 times 2, a sub 4x. All right, so we need to evaluate these at x equals 0 also, because remember the whole point here is I want to set the y coordinates equal. So here I know that the y coordinate of e to the 2x at 0 is 1. What happens if I plug in 0 to my equation here? What's the y coordinate? Well, notice what happens. If I plug in 0, this term will be 0 because it's being multiplied by x. This term will be 0 because it's being multiplied by x. That's got an x in it. That's got an x in it. So really, when I plug in x equals 0, all these terms drop out except for this one. So when I evaluate this at 0, I get a sub 0. And now I've solved for my first coefficient. I've solved for the number that needs to go there. Okay, let's look at this one. If I plug in 0 to the first derivative of my polynomial, all of these terms have a 0 in it, so they all disappear. So p prime of 0 is just a sub 1. So now I've solved for the number that goes here. Okay, we can keep going. So the second derivative, let's evaluate that at 0. So this has got a 0 in it, that's got a 0 in it, so I've got 2a sub 2. So in order to solve for a sub 2, I would just need to divide both sides. All right, third derivative, I plug in 0, that goes away, so this is 3 times 2a sub 3. And then my last derivative, my fourth derivative, this goes away because it's a constant. So I've got 4 times 3 times 2 a sub 4. And so that's 4 times 3 times 2 a sub 4. All right, so these things I've boxed in the middle, these are the results of this conceptual heart. I set the y values equal and I get this. I set the first derivatives equal, I get that. Second derivatives, I get this. So now I can solve for each of these different constants. I've got that a sub 0 equals 1, a sub 1 is 2, a sub 2, I'll just divide both sides by 2, so I've got 4 over 2. A sub 3, I'll divide 8 by 3 times 2, so 8 divided by 6. A sub 4, I've got 16 divided by this, which is 12 times 2 is 24. And so now I can take those coefficients and I can rewrite my original polynomial, only now with numbers. So my final answer is e to the 2x is approximately 1 plus 2x plus 4 over 2x squared plus 8 over 6x cubed plus 16 over 24 x to the fourth. So that's a fourth degree approximation of my original function. What would be nice is to identify a pattern so that instead of continuing to take derivatives here, we could have a general rule that would let us predict what each of these coefficients were. So let's go back and look at this process. So on the right-hand side here, I guess I could write 1 and 1. So I see 1, 1, 2, 3 times 2, 4 times 3 times 2. So if I was going to guess what this next one was, it seems like it should be 5 times 4 times 3 times 2. So it seems like these are the factorials. And it actually kind of makes sense. If you're thinking that this is 4 factorial and you think, where did this 4 factorial come from? Think about where my a to the 4th term started. My a sub 4 term started way up here and it went through the following changes. I took a derivative and the 4 came down. I took a derivative and a 3 came down. I took a derivative and a 2 came down. And so then when I take the last derivative, I'm left over with a 4 times a 3 times a 2. So that's the 4 factorial. So if you imagine that I had a 5th degree one out here, I would have taken a derivative and a 5 would have come down, and then a 4 would have come down, and a 3 would have come down, and a 2 would have come down. And so down here, I would end up having 5 factorial. So I think it's safe to say that if we were going to do the nth degree derivative, this would look like n factorial a sub n. So I'm going to draw a line here so that we're looking in general for the nth term. Okay, what about on this side? So on this side, it looks like the e to the 2x is always there, but it seems like every time I take a derivative, a 2 is coming down. So here I have the first derivative, and I've got 2 to the first. Here I've got a second derivative, and I've got 2 2's, which is 4. Here I've got the third derivative, and I've got 2 times itself 3 times, which is 8. So it seems like for the nth derivative, I should have 2 to the n, e to the 2x. And then if I plug in x equals 0, that's just going to give me 2 to the n. All right, well now if I want to take this and solve for the nth coefficient, I get that the nth coefficient is 2 to the n over n factorial. So that would let me immediately write, if I wanted to do a longer approximation, I could say e to the 2x is what I already have. But then let's see. Okay, so for the 5th degree, this would be a sub 5, and I know a sub 5 is going to be 2 to the 5th divided by 5 factorial. And if I wanted to write another one, x to the 6th, 2 to the 6th over 6 factorial. And I could write as many of these terms as I need. So once you've spotted the pattern, it'll be very easy to write all the coefficients. As an exercise, I think you should try and do this whole process yourself very rapidly. So let's say that our function is e to the x, and we're going to find a 4th degree approximation. Remember, the concept is we're setting all the derivatives at x equals 0 to be equal. So derivatives of this and derivatives of that are all the same at x equals 0. So find all the derivatives, plug in 0. Find all the derivatives, plug in 0. That lets you solve for the coefficients, and you're done.